Okay. Okay, I would like to make a short reminder. People who present posters, if you haven't done so yet, remember to present your poster at reception whenever you can. And yeah, with that out of the way, it is my pleasure to introduce Yanli Song, who will talk about geometric quantization for symplectic b-manifolds. Thank you.
Does it work? Can you hear me? Does it work? Oh, okay, good. Thanks for the invitation. Today I'm going to talk about geometric quantization of b-symplectic manifold. This is a joint work with Yanli and Rashama. Okay, so the goal of my talk is to tell you one version of the quantization commutes with reduction theorem for the setting of the b-symplectic manifold. So the theorem, quantization commutes with reduction, has been studied by many people. Many people in this room contribute to this theorem. It is a great success. And this principle, now it's known as a principle, has been proved in many different cases. I will tell you one of them. That is for the case of b-symplectic manifold. Okay, so to begin with, let's first go back to the starting point of the story. So, yes. Suppose M is a scalar manifold. This is the starting point of the quantization commutes with reduction theorem. If M is a scalar manifold and E is with this symplectic form, the omega, and suppose that E is a line bundle with a connection such that the curvature of this line bundle is given by omega. So in this case, we say E is a pre-quantum line bundle. Since the manifold is scalar, it has a complex structure, we can choose a complex polarization. And the geometric quantization from the viewpoint of the physics is that we want to construct a finite dimensional Hilbert space. How do we construct it? We just take the geometric quantization is we just take the space to be the sections of the pre-quantum line bundle E such that it's a covariant constant along the leaves of the polarization. In another word, in this case, you can just take this one to be the space of the holomorphic sections of the pre-quantum line bundle. This one turns out to be a finite dimensional space. And we consider this one as the quantization of the scalar manifold. Okay. And yeah, this is the, then we move to symplectic manifold. So in this case, we only assume that the manifold is symplectic, but may not be a scalar. So it may not be a complex. In this case, one way to define the quantization is using Dirac operator so that it's related to the index theory. How do we do that? The n omega, suppose it is a compact symplectic manifold. Omega is a symplectic two-form. And it's known that this symplectic two-form has a almost complex structure on the tangent bundle Tm. It may not be complex, it's just guaranteed to be almost complex in the sense that J square equal to -1. And together with the symplectic form omega, it defines a Riemannian metric on the tangent bundle. And this almost complex structure, so here almost complex means that this complex structure may not be integrable. And you can consider the complexification of the tangent bundle and use this J, you can decompose this complexified tangent bundle into the 0-1 part and the 1-0 part. And then you take the exterior algebra of the 0-1 part. So this is the S. So S turns out to be a Z2 graded. The Z2 grading here is that the even form and the odd form. So it is the Z2 graded spinor bundle. When I say spinor bundle, it really means that on this bundle, the Clifford bundle of the Tm acts on this bundle. So that at every point, this bundle turns out to be an irreducible Z2 graded representation of the Clifford algebra at that point. Okay, so under this setting, using this bundle, we can define the double Dirac operator such that for any sections, of E tensor with S. E is the pre-quantum line bundle determined by the symplectic 2 form as before. And we can take a connection, then we get a section here, and use the Riemannian metric, we can identify the cotangent bundle as the tangent bundle. And this the tangent bundle acts on this spinor bundle so that it gives you a section here. So the composition of this map, we call it a double Dirac operator, acts on this space. And this operator is a differential operator, first order. It will be self-adjoint. It has it's elliptic. It's a Fredholm, so it has all the nice properties. And you can extend first it's defined on all the smooth sections, but there's way, by some analysis, you can extend it to acts on the Hilbert space, acts on all the L2 sections. So we can define the quantization as the index of this double Dirac operator D. The index is just says because this Hilbert space has a Z2 grading come from the Z2 grading of here. So you can define the index to be the kernel restricted to the positive part minus the kernel restricted to the minus part. So it's this is because the operator D is a Fredholm, so that the kernel is always a finite dimensional. Oh, question?
Sorry, I'm a bit confused. You mean it has a dense domain?
Oh, yes, yeah. So the kernel is always turns out to be smooth because the ellipticity of the Dirac operator. Okay, so that's okay. So this is the defined. So this is the dimension of this one is an integer minus the dimension of this one is an integer. So this is the index turns out to be an integer. We view it as the dimension of the virtual Hilbert finite dimensional Hilbert space. In the case of a Kähler, you can show that this one will always be 0. All the kernel comes from the plus part. You always get a finite dimensional vector space. But in the symplectic case, then it's possible you get something in here. Okay, so use this Dirac operator, use the index to redefine this quantization. Has the will be it was in first we can apply the index theory to compute this number. Secondly, it has more flexibility because you can see if we define the geometric quantization as an index of some operator, then all we need is to construct some Dirac operator acts on the sections. And to construct the Dirac operator, then we need less structures. We don't even need it to be symplectic or Kähler or almost complex. So this is actually we are going to take this viewpoint in our setting later on. Okay, but here it just says that we can redefine geometric quantization as the index of certain operators. And these operators are constructed, actually, every information, every structure you need comes from the symplectic form. Okay. So the quantization commutes with reduction theorem, we need a group reduction. Let G to be a compact Lie group acts on this symplectic manifold, compact symplectic. It's a Hamiltonian. We assume it's a Hamiltonian. Then we have a momentum map from the manifold to the due of the Lie algebra. This little g is the Lie algebra of the compact connected Lie group. And the momentum map satisfies this property. Okay, this is well known, the momentum map. In this case, we know that the Marsden-Weinstein reduction, symplectic reduction, we take the mu inverse of 0 and we quotient by g. Here, I think we need to make it simple, we can assume this g acts free on mu inverse of 0, and 0 is a regular value. But in the most general statement of the quantization commutes with reduction, we don't need this. I think it's due to Meyrinck and Chamard, they deal with the singular case. But one thing we know is that this M0 symplectic reduction turns out to be a symplectic manifold. If the manifold you begin with, this symplectic 2 form omega is integral, means that it is this symplectic form is a curvature of some line bundle, then you will get a symplectic 2 form on the reduced manifold will still be integral. So you have a pre-quantum line bundle also on the reduced space. So that Before you do the reduction, you do the quantization, as we discussed before, because of the group action, the index or the quantization should be a G space. So that is to say, it decomposes into irreducible representation of G. It will be finite dimensional. And of course, you can take the G invariant part. If you take the G invariant part, you get a finite dimensional space. So this is, you first do quantization, and then you do reduction. Reduction on the left-hand side means that you take the G invariant part. You can also do the reduction on the geometric side first, that is the right-hand side. You first do symplectic reduction, on which you get a compact symplectic manifold without group action, and then you quantize it. So that's you do reduction first, and then you do quantization. You get a finite dimensional vector space. And the quantization commutes with reduction tells you the two procedure give you the same dimension of the vector space. So this is the so-called quantization commutes with reduction theorem. Okay, now let me mention some. So this theorem is first proved by Gellerman-Steinberg for the Kähler case. I think this is, as I said, this is the beginning of the story. That is 1982. And when M is, of course, many people contributed to the theorem, and it has been proved in many different situations. I will just list those cases which are most related to my talk today. Of course, for example, this theorem has been proved for Hamiltonian LG space, but that is a different story. Okay, so if it is the compact Kähler, it's the Gellerman-Steinberg theorem. In the compact symplectic case, this proved by Marinken. And when it's a non-compact symplectic, if we assume the momentum map is proper, so in the case, then this is similar for Ma and Zhang. And also, there's a case of spin C. Spin C is a very weak setting. Most manifold, roughly speaking, most manifold, as long as it's orientable, you can say it is a spin C. It's not equivalent to, it's stronger than orientable, but not too much. So in that setting, Pardin and Verne prove one version of the quantization commutes with reduction theorem. And the good thing about the last case is that from this viewpoint, if it is spin C, so spin C, roughly speaking, just tells you on the manifold, you can construct a Dirac operator. So that's why the viewpoint of defining the geometric quantization as the index of Dirac operator will be useful. So that for the last point, you can view this one, quantization commutes with reduction, as a geometric formula to compute the equivariant index of a Dirac operator. So because the last case has nothing to do with the symplectic. But I'm trying to say is that this is still true. Okay, so this is a little history of the quantization commutes with reduction theorem. Any question? Okay, so now what I'm going to, as I said, what I'm going to do today is to tell you how the theorem works for the b-symplectic setting. Okay, so the b-symplectic manifold I'm going to consider today is the following. So let Z to be a collection of embedded real codimension 1 connected hypersurface. And I need to assume that the hypersurface, they may have intersection, but I want to assume that the intersection is transverse. So that transverse in the sense that for any point, if it is at the intersection of several hypersurface, you can always choose a small neighborhood of that point such that each hypersurface is corresponded to xj equal to the 0. So in the simple case, if it's just dimension 2, then this one is good. This one is a good intersection. And what is not good is something like this. So this one is bad. It's not transverse. So we are not going to consider intersection in this case. We will only consider intersection in this case. Okay. So this is yes. Okay. So this is hypersurface. That's a b-tangent bundle. I will denote it by TZN. Is the smooth rank 1 vector bundle whose sheaf is the smooth sections consists of local vector field tangent to the hypersurface Z. And it's known this b-tangent bundle is a Lie algebraic. Okay, for example, what is the b-tangent bundle look like? So suppose for each hypersurface, if Z has a global defining function, which means that you can choose a function xz such that this hypersurface is just given by the zero pullback, the zero set of the function, and that this dxz is the derivative is not equal to 0 when you restrict to Z. So we assume that every hypersurface in this collection has a global defining function. Of course, here you can see if xz is a global defining function, minus xz will also do the job. So that you choose xz or minus xz is equivalent to make of the choice of the orientation of the hypersurface. Okay, I will just fix one defining function for every hypersurface. Okay, so in this case, that the b-tangent bundle will have some term like this one, xz times, so this one vanish along Z. And its cotangent b-cotangent bundle will consist of forms like this one. So this will be singular. As xz goes to 0, this form will blow up, but it still lies in the co-b-tangent bundle. And using this b-tangent bundle, we can define differential forms. So you just extend every setting to the B case. So you can just play all the B differential forms, and you can also define the B Dirac cohomology. So that I will use this term HMZ to define I will use this one to denote the Dirac cohomology defined use the B tangent bundle or the B cotangent bundle. Okay. Let's see one time. Okay, so a B symplectic form, it is, or some people call it log symplectic form, is a closed two form. Symplectic form is closed. And what is the non-degenerate in this case? Non-degenerate, we will just replace it by this condition. So this two form defines a map from the B tangent bundle to B cotangent bundle defined by contraction. It is isomorphism. Then this is the non-degenerate condition. So this is the symplectic form. And we assume mz omega is a B symplectic manifold. And by a theorem of Guattari-Palaio-Ratiu, this is a generalization of the version of the Mazzeo-Melrose theorem. See that this B Dirac cohomology have the following decomposition. If there's no crossing, or the xzi, they have no crossing, then this is the original Mazzeo-Melrose theorem. But if it has a crossing, then we have more terms, because we allow crossing of the hypersurface here. So we have this one. Next I want to tell you how to do the quantization for B symplectic manifold. To do quantization, the first thing we need is a pre-quantum line bundle come from the symplectic form. So what is the pre-quantum condition? So we say this omega is pre-quantizable if, so the omega live in a live in the second B Dirac cohomology. By this isomorphism, we have a projection to this B Dirac cohomology to the original Dirac cohomology, and we denote it by omega bar. If the omega bar of this projection is integrable, in this case, that is to say omega bar corresponds to the first term class or the curvature of some connection on some line bundle E. And in this case, we say E is a pre-quantum line bundle come from the B symplectic form omega or omega bar. Okay, so this is in order to define the quantization, we need this pre-quantum condition. Okay, next. So one observation in order to do the quantization. So as before, in the symplectic case, we say in order to define the quantization, we need a almost complex structure so that we can define a Dirac operator. But every symplectic manifold has an almost complex structure so that we can quantize it as index of some operator. But in the B simplex setting, there's no almost complex structure. The almost complex structure is only, it has almost complex structure on the B tangent bundle, but not on the tangent bundle. So that will be an issue here. So in order to get around of this, we have one simple observation. The simple observation is that this B tangent bundle and the tangent bundle, they might be different. Even in the two-sphere case. In the two-sphere case, if the hypersurface is given by the equator, the B tangent bundle will be trivial. And the tangent bundle is well known. The tangent bundle for two-sphere is non-trivial. But if you direct sum, here R means that trivial real line bundle on the manifold. So if you, let's consider if you have a tangent bundle of a two-sphere, which is non-trivial, if you direct sum with the normal real line bundle, it becomes a trivial bundle. So that we have isomorphism. So here's a simple proof. For the in the simplest case, if the divisor is given by one hypersurface, then that xz is a defining function for this hypersurface. Okay, and we can take vz to be the tangent bundle vector field such that vz xz equal to 1. We can always find such a vz. And let's rho to be a bump function in a neighborhood of z, so that we are really localize this problem to a neighborhood of the hypersurface, such that rho restrict to z equal to 1. Okay, so that how to define isomorphism, we can define this one. This is vz, this is rho times dz over z, this is minus rho times vz, and this is identity. Identity here means that the injection, embedding this tz to tm, because every tz, B tangent bundle, can be embedded into the tangent bundle. So how do you think about this one? So almost in a B symplectic manifold, you cannot glue the two almost complex structure when you crossing this hypersurface, because they are deferred by orientation. So on one side is j, on the other side is zj. But after you direct sum with real line bundle, it gives you more space to do the rotation, so that you can glue this almost complex structure in some way. That is what I'm going to use later on. Not gluing the almost complex structure is that you can connect these two. So, but this construction works for the case when there's only one the surface. But in general, as I said, we allow crossing. There's some intersection between hypersurface. You just do it step by step. So you first do hypersurface, and at each intersection, you can go degree higher. There's a stratification. So you just play this trick again and again. You can show this is always isomorphism. And this isomorphism is canonical up to homotopy. Okay, so that we are going to use this small but useful observation, that the B symplectic form defines the almost complex structure on the B tangent bundle, and we can direct sum with a trivial complex bundle C, and C is R2. Okay, so which is use the previous isomorphism, we can identify the left-hand side as R times R, R direct sum with R, direct sum with the tangent bundle. So R means the trivial line bundle on the manifold. So on the left-hand side, we have our almost complex structure, because we have almost complex structure on TZM and complex structure on C. By this isomorphism, we get an almost complex structure not on the tangent bundle, but on R2 direct sum with the tangent the bundle. So this is known as, actually there's a terminology for this one. This is called a stable complex structure. Stable complex structure means that the complex structure is not defined on the tangent bundle, but defined on the tangent bundle direct sum with the trivial bundle. So that outside the hypersurface, this one can see this almost this stable complex structure turns out to be a almost complex structure. So this stable complex structure is because on the B symplectic manifold you cannot glue almost complex structure, but if you pass from almost complex structure to stable complex structure, it gives you more space to glue them together, so that you can glue them into an almost complex structure. So one theorem we showed is that every B B symplectic manifold in our setting has a canonical stable complex structure up to homotopy. That is what we are going to use to define the quantization. Question?
Yes. When you say that the B-manifold defines another structure, you don't mean uniquely, right?
What?
You don't mean uniquely, right?
You say unique?
Uniquely, yeah.
No. It's the homotopy is enough. Because that is a good thing about the index, because later I will define the geometric quantization as the index of some operator. And by a famous theorem, the index is very stable. If you give it a kick, homotopy, it's all the same. So that I don't have to be rigid here. So that if up to the homotopy, I only care about the index, the dimension of the vector space I will get. Okay. So that I'm going to construct the Dirac operator, use the stable complex structure. So that I will define S as before. The only difference is that the S I defined before come from the almost complex structure on the tangent bundle. But as I said, although on the tangent bundle we don't have an almost complex structure, but after direct sum with a dimensional 2 trivial bundle, it has an almost complex structure. So we can just do the same construction as before, but only apply to R2 direct sum with a Tm or T star M. So that we can define this is a spinor bundle associated to the stable complex structure. And this one also has a Clifford reduction of the Tm. Okay, so as long as I have this, I have everything I need to define the operator, define Dirac operator. So we can construct Dirac operator as before. So we first take a section, and we apply a connection. Connection, we get a section here, and use the metric, we can identify these two, and then we apply the Clifford reduction, we get it back. So this one, again, it will be a first order essential self-adjoint Dirac operator, differential operator, so that it will be Fredholm. So the index, it will be a finite dimensional vector, finite dimensional vector space. So we define the geometric quantization of a pre-quantizable B-symplectic manifold to be this one. And I have to say, because the right-hand side is the index of the operator by the index theory, you can see here, I didn't really make it specific how to choose the metric, how to choose the connection. The point is that since the geometric quantization I defined as the index, so if you choose different connection, it gives you the same. So it does the good point is that if we're defining this way, this number z does not depend on the connection you choose, does not depend on the metric you choose, and only depends on the almost stable complex structure determined by the B-symplectic form. Okay, so this is how I quantize a B-symplectic manifold. Here we can quantize a B-symplectic manifold even there's no group reduction. Given any B-symplectic form, it may have some hypersurface with the crossing. I can use this almost complex structure to quantize it. Okay, in order to state the quantization commutes with reduction. Oh, question?
Yeah, I was just curious. In this picture, you have this extra factor R2 that you added.
Yeah.
To define the complex structure. In the case where the singular locus is empty.
Oh, yes.
Then, if you were to do this construction.
Oh, it will be a homotopy, so it gives you the same index.
And so the Dirac operator is like just the identity on that.
Yes.
I see.
Yeah.
So it doesn't-
Yeah. So now, moderate. Now I will impose a group action on the B-symplectic manifold. So let G to be a connected compact Lie group as before. And suppose this G acts on the B-symplectic manifold, everything is preserved by G. So everything is nice. Everything is behave very nice with respect to G. And for each hypersurface, we can define a residue map from this B differential form to a dimensional lower differential form on the hypersurface, which is defined by this one. Here, EZ is the vector field defined in this way. And you just, for any differential form, you just take the contraction and restrict to Z. And the modular weight is defined as follow. It's a map from Z to the due of the Lie algebra, such that you can see here, CZ is lies in the Lie algebra, X is due of the Lie algebra, X in the Lie algebra, the pair, you get a number. On the right-hand side, the omega is a B symplectic 2 form. You apply the ratio map, you get 1 form. And then you contraction with a vector field. XZ is the infinitesimal vector field induced by the action of the X. So the right-hand side, you also get a number. And this CZ, you can show on every connected hypersurface, it will be a constant. This modular weight is important because how do you think about the modular weight? So that for each hypersurface, the momentum map, in general, it should be proper. But this modular weight tells you it goes to infinity in which direction, roughly speaking. This is my own understanding. Maybe, of course, there may be some other interpretation of the modular weight, but this is modular weight will play an important role in the b-symplectic manifold. Okay, so that is to say, for every Z hypersurface, I can associate, because CZ, although it is mapped from Z to the due of the Lie algebra, but turns out it is a constant. So that is to say, for every hypersurface, we can associate with a weight. Okay.
It's a modular. It's a modular vector field.
Yes. Oh, yes. Thank you. Yes. Of course, you know this better than I do. Okay. So, what is a Hamiltonian G space? What kind of Hamiltonian G space we can quantize, and which kind of Hamiltonian B Hamiltonian space satisfy the quantization commutes with reduction? We still need some very mild assumption. So what we need is that, suppose the G action is Hamiltonian in the sense that the momentum map is proper when you set minus all the hypersurface, but you ignore those hypersurface with zero modular weight. Let me make one comment here is that if there's no intersection, I think if there's no intersection, then the modular weight is either all non-zero or equal to the zero. But if we have an intersection, then it's possible some modular weight equal to zero, some modular weight are non-zero. And we only require this momentum map to be proper when you take away those hypersurface whose modular weight are non-zero. So for those hypersurface whose modular weight is non-zero, you want it is the momentum map goes to infinity when you approach those hypersurface, and it will goes to infinity towards the direction given by the modular weight. We want it to be proper. So this condition is something like this. So for example, in the two-dimensional case, so this momentum is proper. So that is to say, it will when you approach this hypersurface, it will go to infinity. When you approach this hypersurface, it also will go to infinity. But in order to make it proper, in another way, it just depends on the position of the modular weight also associated to this two hypersurface. For example, if it goes to infinity, goes to the positive direction, it goes to negative infinity towards here, then when you approach to their intersection, then the momentum map will be failed to be proper, because when you approach here, it's like the linear combination of something large, something very positive, something very negative right here. So that is to say, this assumption, the momentum map is proper over here, is equivalent to say that all the non-zero modular weight form a convex space, linear the combination. So that is to say, in a dimension 1 case, you cannot have a positive modular weight and a negative, another is negative. But if they have no intersection, that's fine. But if they have an intersection, then for those hypersurface has intersection, what you need is that the modular weight form a convex set. Okay, so this is equivalent to say this momentum map is proper. Okay, so when you remove those hypersurface, you will get a non-compact manifold. And this momentum map is defined over here, and we have this one. So it has a momentum map satisfy this property. And what we showed is that because we want to quantize it, although the momentum map is proper, but it is a complex manifold with a stable complex structure. So if you forget about any symplectic or the singular forms, it's just a compact manifold with with a stable complex structure. You can quantize it. You can define Dirac operator. Its index will be finite dimensional, so the quantization will give you an element in RG. RG means that it is a character ring, or it is a finite linear combination of irreducible representation of G. So it's guaranteed if we use the almost stable complex structure to quantize it, it's guaranteed its quantization will be finite. Okay? And another way to think about this one is that because omega bar is the regular two-form, it may not be symplectic. You obtain it from the projection, from the B Dirac cohomology to regular cohomology. You can always modify the momentum map. The momentum map is not defined on the whole manifold because it goes to infinity when you cross the hypersurface. But you can always modify using the modular weight. To modify the momentum map, we get a mu bar such that it satisfies this property. So what you will get is this manifold with this regular two-form. It may not be symplectic, and some momentum map, not quite, some momentum map, which is defined everywhere on the manifold. This one will be a pre-symplectic Hamiltonian G space. So what our quantization is just to quantize this one. Okay?
Question.
Oh.
If you consider, well, first the group, the group has some constraints. You cannot have any group.
So the group has what?
Has to have some constraints, right? You cannot have any group acting there.
Oh yes, it's actually compact connected Lie group will be okay. We don't need to be.
Yeah, but assume that you have a group of rank maximal rank. The fact that you have a certain geometrical structure on the critical set, which is this mapping torus, imposes some restrictions of how the group can be.
Oh, I think for compact Lie group that should be because I said, okay.
You need to have some restrictions. So you need to have an S1 action, which is associated to this modular weight. And then my question is that you can consider the reduction with respect to this S1 action in a covering. And then you may use quantization commutes with reduction in the reduced space.
Okay, actually, yes. Okay, I will.
Yeah.
Maybe we can discuss after.
Yeah.
Yes, I think, okay, you think.
Because there is some work by Guillermin Miranda and Weitzman on this topic.
Yes, I remember in your paper you described this one, but yeah, I need to refresh myself too.
Good, thank you.
Okay, so one example will be this one. So let M to be a two-sphere, then this is a hypersurface, but this hypersurface is not on the equator, it is on A. A is the height from -1 to 1. So A is a number. So that the P tangent bundle is trivial. So the hypersurface will be a circle. And this B symplectic form is given by this form in this way. It has a singular along the Z equal to A. And the group to be this one acts on the manifold by rotation, and it's generating the vector field is given by this one. Just give the by rotation. In this case, the modular weight is -1. Is a -1. Okay, and the momentum map is turns out to be this one, just minus log Z minus A, and with some shifting, you can always shift this momentum map, but it always satisfies this property. Okay, so this is one example of a B-symplectic manifold, and if A equal to 0, I think in Richard's talk, the quantization should be 0. But if you choose A to be other number, then the quantization may not be 0. And this is what I'm going. So you can see, you can ask for any A. So you can ask when this symplectic form, B-symplectic form, is integrable or pre-quantized. So that is to, it's equivalent, by some work you can show this equivalent to say this is pre-quantizable if the integration from -1 to 1, z minus a dz. Of course, they have a the singularity along a, so you take the principal value. You want the principal value to be an integer. So if you take the principal value, what you get is this one. If this one is in z, then it is pre-quantized. So you should view this n as the symplectic volume in some sense. So that is to say, a parameter, if you wanted to quantize, so that is to say, when this pre-quantum, this space is pre-quantizable, then you can not choose any a, but this a, you can choose a countable many a from -1 to 1. In this case, let's suppose this momentum map restricts to the north pole and the south pole to be n1 and n2, because the north pole and the south pole are given at the fixed point. So if we have the line bundle, then by the constant formula, the momentum map should be the integer. And it's guaranteed that n1 minus n2 equal to n. And you can, as I said, in the previous page, the momentum map, you can have this shifting of a prime. It always satisfies this property. You can choose the a prime such that the mu equal to this one, and mu equal to n1 at z equal to 1 and equal to n2 when z equal to -1. So if you chop this sphere into north hemisphere and south the hemisphere, then the image of the momentum map will be n1 to infinity. This is the S2 plus, means the north the hemisphere, and S2 minus is the south the hemisphere. Each one is a non-compact symplectic manifold. And the image of the momentum map is from n1 to infinity and n2 to infinity. And if you use almost complex structure, or in terms of what you get is you can actually, in this simple case, you can just use the T-Abbott fixed point theorem to compute it. So the index will be t to the power of n1 minus over 1 minus t minus t to the power of n2 over 1 minus t. So this one will be just a linear combination of this power of t. You can view it as the Fourier modes, or this is what you get is a finite linear combination of the finite representation of the circle. And okay, let me make one remark, is that this formula is slightly different. Well, actually, it's different, very different, not slight, different from the T-Abbott fixed point for sphere, for the regular sphere. The reason is that if you look at the denominator here, this is 1 over t. This is a contribution from the north pole. This is, again, 1 minus t. This is contribution from the south pole. If you apply the T-Abbott to the two sphere for not b-symplectic, just the original symplectic, then what you get should be 1 minus t, the inverse. The reason these two denominators are the same is that the two complex structure on the two sides, they are the same, so that you cannot glue them together. But if you restrict to the north pole and the south pole, they are the same. So this they cannot, the almost complex structure cannot be glued together because they are differed by orientation. Okay, so this is one example. Okay. Now let me state our main theorem, that we assume the momentum map to be proper. We assume this momentum map is proper, that we allow, so that if this divider has no intersections, then this momentum will automatically be proper. Not when I say proper, means that proper when you remove all those hypersurface with non-zero modular weight. Okay, and for simplicity, we assume this ejection on mu inverse of 0 is free. Okay, so in this case, as I said, because I allow the modular weight to be 0, so the reduced space will be a b-symplectic manifold. It's in general, it may not be. It's possible because the hypersurface with 0 modular weight may intersect with the mu inverse of 0. So that the reduced manifold in general, it may not be a symplectic manifold, but a b-symplectic manifold. So that if it's pre-quantizable with Hamiltonian ejection, then the reduced space is a compact pre-quantizable b-symplectic manifold. Then we have this, the quantization commutes with the reduction. So the left-hand side has take the G invariant part. Okay, so this is the result for the quantization commutes with reduction for the b-symplectic manifold. Okay. Okay. So in a special case, when there's no crossing and the modular weight are all non-zero, this is one setting considered in Gellerman, Miranda, Weitzman's paper, then in that case, the geometric quantization can be defined in use other method. So because in that case, you can just, if you remove this hypersurface, you have only one hypersurface. If you remove the hypersurface, you can break this b-symplectic manifold into union of two non-compact symplectic manifold with proper momentum map. So one way to define the geometric quantization is that you can use the Melrose B calculus and or the Atiyah-Padodi single index theorem, because what do you get? You can view it. You can view it, break it into two symplectic manifold with a boundary, or you can view it as the union of two non-compact symplectic the manifold. Depends on how you are going to view it, and or you can use that Mahjong's approach to the geometric quantization of a non-compact symplectic manifold. You can define the quantization in this way, and you can show that in this case, if you use these two methods to define the geometric quantization, it will be consistent with the definition using stable complex structure. And let me make one remark: is that if you use the B calculus or the Atiyah-Padodi single index theorem, in fact, one interesting or the most interesting information in the Atiyah-Padodi single index theorem is the eta invariant, which is not topological invariant, but depends on the metric near the boundary. But in this B-symplectic setting, in fact, the eta invariant, because what do you get? You get a two manifold with a boundary. The eta invariant, they cancel. So you won't be able to see the eta invariant in a quantization picture. So one thing I'm curious is that what the eta invariant says in what kind of symplectic information, or what can we say? What kind of information we can get from the eta invariant? Okay, I don't know the answer, but what I'm trying to say is that if you use this manifold with boundary to define the geometric quantization, the eta invariant, they cancel. You won't be able to see it. Yeah. Okay, so in general, if there's a crossing, then this two does not work very well. It probably, if you won't work very hard, can make it work, but at least we have some difficulties that if you use this two approach, you have to deal with the manifold with corner, not just with the boundary. So if it has a crossing, and also if the modular weight is 0, if for some hypersurface modular weight is 0, then the reduced space is still a b-symplectic manifold. Is still because, as I said, in that case, the mu inverse of 0 will intersect the hypersurface with modular weight. But as I said, although it's just the reduced space is again a b-symplectic manifold without group action, but it still has a stable complex structure, so we can still quantize it. Okay. Okay, so here's the idea of the proof. Once you, since I formulate the quantization, use the index theory, I can just use the index theory technique to prove. The proof is similar to the proof of the quantization commutes with reduction for classical symplectic manifold, so that we can have a current vector field induced by this momentum map. This current vector field is not defined everywhere because the momentum map is only defined away from the hypersurface. But the vanishing set, you can have a vanishing set of the vector field, of the current vector field, and by the property of the momentum map, that this current vector field, the vanishing set of the current vector field have this description, where this beta is just a finite set. Oh, I think in this case, it may not be a finite set, and it is just yeah, I think here the beta is just a finite set because M is compact. Okay, and what we do is that the only new ingredient in the proof of the quantization commutes with reduction in this case is that we modify this current vector field so that extends smoothly to M. The current vector field is defined away from the hypersurface, but you can always modify it. Actually, in order to modify it, you really need to use the modular weight to modify it, and such that it's a global vector field on the manifold, and you want to modify it carefully such that it has the same vanishing set. And then, because the quantization, we define it as the index of the operator, we have all the technique, all the result from the index theory, we have some localization. You can always localize to a neighborhood of every vanishing set. And what you need to show is that for all U beta is just a neighborhood of this vanishing set. So for every beta, you can associate it to a neighborhood. And you can first localize to the neighborhood, and you want to then, by some work, you want to show that for all U beta, but beta non-zero won't contribute to the trivial representation. So that if you wanted to compute the multiplicity of the trivial representation of the quantization, you only need to localize to U of 0. U of 0 will be the neighborhood of mu inverse of 0. So that is how you do the localization to the mu inverse of the 0. And by some assumption, if you know some more geometric structure near mu inverse of 0, you can do further reduction to relate that to the reduced space. So this is so here the new ingredient is to modify the kappa, the current vector field, using the modular weight. Okay. So that. Here's one way is that if lambda is an integral weight, the shifting trick also works in this setting. With some mild assumption, you can make the shifting trick. Shifting trick means that the result we discussed so far is a reduction at the 0. 0 is a co-adjoint orbit or integral weight, and you don't have to deal with you can actually reduce the manifold not at just 0, but at other integral weight, so that we can define the mu lambda to be mu inverse of the lambda over g lambda. G lambda is a stabilizer of lambda. Lambda is element in the Lie algebra of T. T is the maximal torus of G, and in this one will be this reduced will be again be a b-symplectic manifold. So that using this, we can actually, this is due to Gellerman, Miranda, Wetzman, they defined a formal geometric quantization. You can use the reduced space, because for every reduced space, you can quantize it, you get a number. So you can get the formal geometric quantization is you define the quantization in terms of the reduced space. And but here, that as I said, because in our case, we provide a way to quantize the b-symplectic manifold, even where there's no group action, where the modular weight equal to 0, so that we allow this CD to be non-zero. So on here, in their setting, in Gellerman, Miranda, Wetzman setting, I guess I remember in their setting, the reduced space is a symplectic manifold. But here, we don't need the reduced space to be symplectic. B-symplectic is enough. Okay, in this case, one can, under some assumption, we can show that the quantization commutes with this is the quantization, and this is equal to the formal quantization. So this is the extension of the quantization commutes with reduction from reduction at 0 to reduction at all co-adjoint orbit. Okay. So my last slide is one application to the toric log symplectic manifold. So I'm not an expert on this, but here's one can say that the toric symplectic log symplectic manifold has been defined and classified by Gellerman, Miranda, Perez-Scott for the case without crossing, and Guattaro, Lee, Pelayo, Ratiu for the case with crossing. Okay, I hope I'm correct. So then in this case, that is for those toric symplectic manifold, I think they prove the Delzan type theorem. That is to say, the symplectic manifold, the toric symplectic manifold can be classified by the image of the momentum map. So that in this setting, we can suppose M omega z is a toric log symplectic manifold. And in that case, because it's b-symplectic or log symplectic, the image of the momentum map is no longer live in Lie algebra. because they have singularity. So what you do is that you want to glue several Lie algebra together. That is where the image of the momentum map take value in. So let sigma to be the space constructing by gluing together copies of the compactification of T star. T star is the dual of the Lie algebra T. And this T is some normal crossing divider. And this delta, we let it to be the admissible log affine polytope in here. We view this lambda as the image of the momentum map. So now the image of the momentum map, I think it has a name. This sigma is a tropical weighted space. I think that is the name, just gluing of several copy of T. And in this case, it's, this lambda is a polytope in this space. And we can apply quantization commutes with reduction to this case. It just says that the quantization, if you quantize this toric manifold, its quantization can be is completely determined by the image of the momentum map. So that is to say, of course, we need some assumption. We need some a condition. Then the multiplicity of this C lambda in the quantization equals 2. So for each lambda j is the connected component of the image of the momentum map intersect with this. The image of the momentum map intersect with each copy of sigma I. Sigma I is one copy of T. So that you want to see. So what you get here is so every lambda, every delta j could be a non-compact, not polytope, but a convex cone. In this, and then you intersect with the integral weight. So this lambda is the set of the integral weight in T that you want to see lambda lies in here or not. But since you have to worry about orientation, so that you need to throw in OJ just plus or minus, depends on how you cover this space. So that is to say, you can the quantization of this toric symplectic manifold is completely determined by the weight covered by the image of the momentum map. But of course, here you need to counting the plus or minus sign. This is one application of the quantization commutes with reduction to toric symplectic manifold. Okay. So this is the end of my talk. Thank you.
Okay, are there more questions for Yanli?
Thank you for a nice talk. So you mentioned that in principle the reduced space may also be bisymplectic.
Yep.
What are good examples, or what is your preferred example of such a situation? Is there in general a good source how you can produce?
Yes, as long as the modular weight is non-zero. Oh, sorry, if there's a hypersurface whose modular weight is 0.
Yeah, but how I would build such an example concretely if I want to have some interesting and simple example?
Okay.
What would be the setup?
For the construction, I don't know. I think maybe there are some other people in this room know this better than I do, how to construct, given some modular weight, how to construct those examples. Actually, I don't know the answer, but
okay, thank you.
But I believe there should be a way to construct this.
Oh, sure.
Could you go
I
back
can
to...
answer.
Okay. Oh, sorry.
Simultaneous. No, you go on first. No, I just wanted to comment, like the question of Anton. Like, of course, if you have if you have a modular weight that it's non-zero, either all of them are 0 or non-zero. This is something we proved with Victor a long time ago. Then, when you do the quotient, then it's going to be symplectic, and then indeed you can recover this result from the classical quantization commutes with reduction. And a good source of examples would be that, for instance, that come from any Hamiltonian action on a, if you think of the B tangent bundle, like a Lie algebroid. And then what you are doing, so essentially you are doing just a reduction. If you look how is the critical set, then you will be doing a reduction on the symplectic leaf on this critical set that it's a mapping tori. So so a good source of examples is that indeed it's a theorem that if you take any group action on these symplectic leaves, then you can extend it globally to produce examples. Indeed, with Anastasia Matviva in her thesis, we have produced lots of examples in that direction. Yeah. So, well, I just wanted to comment this.
Thanks for the help.
We'll talk about this.
Is it working?
Indeed, there is an interpretation of this last result, but
Does this work?
Yeah, I can hear you.
Testing? Testing. Oh, okay. I just wonder, could you go back to the slide where you show the equality with the formal?
Okay, okay. Is it this one?
The equality with the formal quantization?
Oh, okay, here.
Yeah. So on the left-hand side, that's your quantization, which is
The left-hand side, yes.
which is the index of a Fredholm operator. So it's
Yes.
the difference of two finite dimensional
Yes,
vector
yeah.
spaces. On the right-hand side, you have a sum of infinitely
Yes,
many
yeah.
spaces.
But it turns out to be
So what does it mean to say that they're equivalent?
Oh, they are the same because okay. So first one is that the right-hand side, it's not obvious, but turns out because the manifold is symplectic, so it turns out, although the right-hand side is defined, if you, at the first glance, the right-hand side you think is a linear combination of infinite many, but turns out there's some cancellation. You will always get a finite. So this inequality is the inequality as the...
Okay, but my question is about the cancellation.
Oh,
So
okay.
what is the mechanism by which the cancellation occurs?
Yes.
And therefore this equality would make sense? Because
Oh.
otherwise it doesn't make sense.
Yes,
right?
of course. The cancellation, simplest case is you can think about even the simplest case, this how to say the two sphere with hypersurface, and because the momentum you have a momentum map, which is what I'm trying to say is that it's proper on both sides. But it turns out the mu inverse of, for example, this every m lambda. In that case, where there will be 2 points. So that when lambda is large enough, it will be 2 points with different orientation, so they cancel.
So I understand that you're explaining why we should expect the cancellation to occur, but I'm just wondering, when you prove a theorem like that, right, is there an operator that's acting on the right-hand side?
Oh, on the right-hand side. Okay. Oh, on the right-hand side. No. It's so on the right-hand side, there's no operator. This is just equality in R of G. But the operator acts on completely different space. So the left-hand side is operator, Fredholm operator. No. Oh yes. Yeah. 2 element. Yeah. Oh, so both sides is the last. So in order. Okay, so maybe I can explain in this way. So the left-hand side, you can embed RG into this infinite sum, right? So that is to say, you can view both sides as the equation in the infinite linear combination of R of G, which still makes sense. But turns out it is always the case, both sides has only finite linear combination. Does this make sense?
But the formal geometric quantization, I think that Marco is saying that when we define it, we were assuming that the modular ring is
Yes.
Otherwise, we don't have this cancellation.
Yes.
Otherwise, it doesn't make sense.
Yeah. Yes.
And indeed, this is also what you would detect if you look, well, in the toric case in particular, you have this as well, actually, because you're assuming this toric.
Yeah.
So then you have a finite sum. So
Yes.
the question is, what happens, for instance, if you have a semi-toric manifold?
Yes.
Would you still have the equality?
Yes,
I mean, with PAL, we are doing something in this direction.
Yes,
The last result that you showed was proved last week. Thank you. The last result that you showed that you. So in the summer school, we had a course by Jonathan Weitzman where he was proving this last result, but he was doing it like we did with Palmir. It's like a joint collaboration. And then this makes sense, let's say, because it's storic, then you have this as one action. But would it make sense that this equality holds in the case in which the modular weight is 0?
Okay,
That's the question.
I see. Actually, I don't know. I need to think about it.
Yeah, that's interesting.
Hi. Sorry, I promise I will be brief. In this R2 plus the B-tangent bundle that you presented, I wonder if you thought about the algebroid structure there, or if there is one, and if this happens to be something called symplectically algebroid. So each fiber has a symplectic form and is compatible.
Each fiber has a symplectic form.
In this case, it would be the canonical one on R2 and the one that you have on the B-tangent bundle.
Oh, I didn't thought about that. So are you saying that consider R2 times B-tangent bundle, with that has a symplectic form?
Right, on the fibers.
Okay, I don't know.
Again, I think the remark is to what extent certain constructions can be extended to symplectically algebroids, which are these kind of
that's
objects.
possible. That's possible. That's possible. Yeah, but I never thought about that way. Thank you.
Okay, thank you.
Hi, so at some point you said that you can project the bisymplectic form into a smooth one which is closed. I guess it's pre-symplectic or something like that.
Yeah.
And you said you could construct a modified moment map.
Yes, yeah.
Like, can you comment on that? Because
yes, actually, we gave a very explicit construction. How do you get the omega bar from omega? It's just you choose some like bound function and make some modification near the boundary, and then how you explicitly construct the omega bar will tell you how do you explicitly construct a mu bar from mu.
I see.
So because, yes, it's just, as I said, because the mu is not defined, it has some singularity
So
along the hypersurface. Then you just modify it, use the log function in a suitable way. Actually, you can make it very precise.
Okay, thank you.
Thank you.
Thanks for the talk. Yanli, question. So basically what you do is you start with your b-manifold, you construct a Dirac operator on that, right?
Yes, yeah.
So basically you're constructing some spin C structure.
Yes, exactly.
Right? And then corresponding operator, and then you are looking about, and if it's equivariant, you look at its image in homology of a group, right? In the group ring.
Right.
And then you are really computing the image, right?
Yes, yeah.
So there are these standard formulas for this kind of computations.
Yeah.
How is that related to these formulas? There are standard, it's Berlin, Getzler, for example. So they have formulas where they write down this index.
Oh, yes.
Explicitly, right? Where they where they tell you how to compute the coefficients.
Yes.
So how is this related to what they wrote?
Actually, we didn't do towards that direction, but yes, this is something we thought about it, and so I guess one natural approach, or actually we have in my mind, but we didn't really do it, but is that...
because these are these formulas.
Oh, but if you ask this one, I think this is actually, your question actually makes sense even for symplectic manifold. Does not have to be symplectic. I think it's just, I think these are two completely way to, because it's
the same formulas.
But
right?
completely, but with respect to completely different localization.
Different what? Sorry.
With a completely different the localization.
Localization.
Localization is that, for example, if you have a Lie algebra, so in the Berlin Wern's formula, you have a Lie algebra. For example, in a torus case, you always localize to the fixed point.
Well, that's more or less what you are doing, right? No, you are doing similar thing here. actually, right?
Yeah, but
So you take C of M cross group and you're splitting into
but I saw that.
K-theory classes,
Yes,
right?
yes,
So
right.
it's basically the same thing.
Yeah, they are computing the same thing, but the formula are different. For example, to
They
compute
cannot
the
be different. The
Oh,
result
they are
has
the
to
same.
be the same, right?
They are the same. But why they give you the same multiplicity or the coefficient?
No,
Actually,
but that's because you are computing the same thing.
yes, exactly. Yes, yes.
Right?
Yeah, but use different method.
Okay, I don't know. Okay, thanks. Maybe we should talk about it later.
Okay, I'm happy that we had such a rich discussion. Let's thank our speaker again. Now we are supposed to have a 10-minute break, which has already finished. So we'll have a 5 minutes minus epsilon break so that we have time to set up Francis Wischhoff's talk. Thank you.